Realization of basic gates using NOR. Keep in mind, this video builds on the previously released video on NAND gates. Not using NOR. Okay, first I go to my circuit tutorials. I find my NOR gates circuit tutorial. I show the diagram and oh, it's a bit different. Now it's output, input, input, output, input, input. Okay, we can work with that. We go back to our trainer kit, and now when we add our IC of NOR gate, we now know this is the output and these are the inputs. Alright, let's connect our VCC and our ground first and check once with the diagram if we've done correctly. We have. We go back to our trainer kit, and now according to the diagram on the right, the same input gets connected to both the channels and the output is the result of our NOT operation. So I take my input, I connect it to this channel, I take my input again, I connect it to this channel, I take my output and I connect it to that, I power it on and voila, it works. Or using NOR. Well, basically, NOR is just the opposite of OR, not OR. And like NAND, if not OR is NOR, then not OR is OR. So we take the NOR operation as shown in the diagram and then we pass it through a NOT gate created using NOR. So I'm gonna add my IC, add my NOR IC, connect the VCC, connect the ground, and now as per the diagram, connect my first input to the first NOR operation, connect my second input to the second NOR operation, take its output and then connect it to another NOR operation and again to its next input line, and the output of this becomes my OR operation. Power it on, boop, 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 boop. There we go. And using NOR. As per the diagram, first we take the first signal and put it through a NOT gate created using NOR. Then again we take the second signal and put it through another NOT gate created using NOR, and then the result of these two outputs are passed on to another NOR gate. It's a lot like OR using NAND. It's just this time we're making AND using NOR. I'm going to add my IC, do the first operation first, now do the second operation, and now do the third operation. So I take the output of my first operation, I take the output of my second operation, and now I take the output of my third operation and it becomes my AND. I connect my VCC and my ground. If I power it on, boom, it works just like that. XOR using NOR. If you look at the diagram, it's exactly like XNOR using NAND. So if we've done that correctly and we compare it to NAND, we have one more gate here. Like in NAND, XNOR has one more gate than XOR. Then let's add our NOR IC, and the first operation is the combination of A and B. Quickly go ahead and do that. Now, the second operation is the output of the first operation and the first signal. So we take the output, we put it over here. We take our first signal, we put it over there. Now the third operation is the again output of the first operation and the second signal. So we take that, we put it over here, take a second signal, we put it over there. Now lastly, the fourth operation in this IC gate is the output of the previous two operations. So I take this over here, I take this over here, and this becomes my operand output of these four IC gates. Now we need to add it to a NOT gate created using NOR. We've run out of gates in this IC, so we quickly add another IC, take the output over here, pass it through here as a NOT gate, and the output of this comes our XOR operation. We quickly add the voltages to both our ICs, and then we quickly connect the ground to both our ICs. Having done so, if I power it on, it works flawlessly as a XOR. XNOR using NOR. Now remember, XNOR is basically the opposite of XOR. If we look closely, we are taking the output of our operand in this first IC and passing it into a NOT gate. Now, according to this diagram, there is no need to do that for an XNOR created using NORs. And that makes sense. Instead of reversing the output again, what if we just remove the first reversal of it? Let us go ahead and do that. Remove the connection here, remove the connection here, and remove the connection here. Then we delete our voltage and our ground for the second IC, and we have no more need for our second IC. So we remove that. Now, this was the output of our first four operands. And this diagram is exactly what we have here. It's just that previously we had extra one more step. And instead of creating another NOT gate, so instead of doing not NOT, we just simply removed the first NOT. NOT of 1 is 0 and the NOT of 0 is 1. So if I can already get 1, why would I pass that 1 into a NOT operation to only create another NOT operation again? I'll just simply remove the first NOT operation so I have 1 with me by default. So I take the output and I put it over here, and we have a flawless XNOR gate in our hands.